So today what I'm going to talk about is Anomalib and how we can bridge the gap between the research and the real world applications and industry. More specifically, the challenge at CVPR in regard about visual anomaly detection. So since the theme of this talk is more robotics, maybe I can start with this video that my colleague Paula created. So, this is quite common in industry that we see, especially in industrial and manufacturing, that we're deploying models, to use robots to automate process. So this is kind of an exemplary demo showing how we can utilize robots and deep models for anomaly detection or defect detection kind of problems, which is quite common in industrial and manufacturing and retail. There are so many different applications that we can utilize robots and deep models to find defects, basically. Yeah, this is a bit of a quick introduction, but now what I want to do is to focus on the problem that we're facing when we apply these models in the real world settings, which is the data sets are highly imbalanced. For example, when we look at this example, which is kind of demonstrates how defect detection could be applied in chip industry or quality assurance and things like that. So there's so many normal samples we can come across, but few abnormalities, which makes the data set significantly imbalanced, and that kind of adversely impacts the overall performance of the models. And what's even worse is that the abnormalities are often unknown and or they can change or evolve over time. So whatever is normal today might be abnormal in the future, or that we could have some new abnormalities that we might come across and so on. So, for example, there's different types of defects here, and this is not limited to these defects. So, like, in the next day, there could be some other defect that, we may never see before. So this kind of shows that we kind of need to learn the normality to find out what abnormal or how abnormals could differentiate from the normal ones. So this is how we and why we introduced Anomalib, which is a library to design, develop, and finally deploy deep learning anomaly detection algorithms. Maybe I can quickly go over the key features. So the library or the framework itself, it contains a number of state-of-the-art anomaly detection tasks and models. It provides an API for customization. So let's say you want to use something off the shelf, so you can use the state-of-the-art models, but let's say you want to design completely new or something on your own. You could utilize the modular API. Or let's say a user would like to just utilize a command line interface instead of diving deeper into the code base. They can have access to this fully configurable CLI. And at the end of the machine learning cycle, after training and testing and so on, the framework itself provides a number of inference interfaces for deployment at the edge. So that kind of shows that the library provides features for the entire machine learning lifecycle, all the way from data collection to the deployment. The library that currently supports image, depth, and video, mainly focusing on the visual anomaly detection, but we have some ongoing efforts to support some other domains as well for multi-modality perspective, which is like time series, audio, and some other domains as well, which are getting quite popularity in the industry. And in terms of the supported tasks, Anomalib can do classification, detection, or segmentation, meaning that we can find or predict the anomalies on an image level, or maybe more localized bounding box level, or maybe pixel-wise mass predictions. As I mentioned previously, the Anomalib supports a number of state-of-the-art algorithms. If we look at the taxonomy, we can see that we have one class training-based models, meaning that the models only utilize normal images during training and use normal and abnormal samples for validation and test. So that give us the opportunity to not have anomalous samples during the training, but focus on the normal samples. So this way we can learn what or how normality looks like for the data set that we have, and then we can focus on how an anomalous image looks like. And within the one class training itself, Anomalib supports feature embedding based models and reconstruction based models. And for the feature embedding based models, we have knowledge distillation models, distribution maps like normalizing flows, or memory bank based models. For the reconstruction based models, autoencoder, encoder, decoder based models, generative adversarial networks, and so on. So these models are all published at top conferences like CVPR, ICV, CV, and so on. In addition to one class training, Anomalib also recently introduced a new zero few shot learning stuff, following the new advances in large vision models and multi-modality. And we have a baseline model, WinClip, which was published at CVPR last year. So this way we can don't need a training, but basically just perform a zero shot and find out the anomalous samples. All right, so let me talk about the high-level workflow in the library. So how a user or a developer can perform an end-to-end machine learning life cycle all the way from training to deployment. So basically, as I mentioned, the images are so the models are trained using normal images only. So we have an unsupervised or sometimes semi-supervised training framework, and following this approach, we have a trained model. And for the validation and test, we have both normal and abnormal samples to differentiate normals from abnormals. So to do so, we do some sort of adaptive thresholding, followed by matrix logging. And the third stage is the model optimization stage. This is quite useful if you would like to deploy your models at the edge for industrial applications, right? Many models are quite complex computationally. So optimization stage would help us to make the model significantly faster to run on the edge. So model optimizer stage would utilize OnNX and OpenVINO to make these models quite efficient on especially small devices. And when it comes to deployment, we provide a number of deployment interfaces like Torch or Lightning, OpenVINO, Gradio, OnNX, and so on. So depending on what the user wants and their requirements, they can utilize these interfaces. Right. So let me briefly talk about the high-level architecture. So we have both CLI and an API, as I mentioned, and a number of components within the framework itself. And these are data modules, models, callbacks, matrix, and visualizers, and the engine component. So the engine component is something that orchestrates all these data modules and models and the rest of the components. And this pipeline utilizes PyTorch Lightning, so it's pretty similar to the Lightning trainer, but it also provides more advanced functionality. And this engine has entry points all the way from train, validate, test, export, high parameter optimization, and benchmark. So start with training, go all the way down to the benchmarking the models. All right, so I talked about how the workflow is and the architecture looks like. So let me briefly talk about how easy it is to install the library. So basically, a user can just download it via a pip install, And for those who would like to make this installation even more hardware agnostic, such as like, installing the right version of Torch, not CPU version, but maybe the correct GPU version, if GPU, like which GPU, which hardware more specifically, and so on. So they could just utilize Anomalib install subcommand, and that's it. All right, so let me briefly talk about the entry points. So we both provide API and CLI. So as I mentioned previously, so for those who would like to use API, they can use the API code base, or for those who would prefer CLI, it's also available, and it's like one-to-one parity. So let's say you would like to use an API. So basically, what you need to do is basically import the data, import the model, import the engine, initialize these components, and then just call the train entry point by passing the data and the model. And with these couple of lines, we can easily train a model on the data set that we provided. If we would like to do the same thing via CLI without diving into the code base, that's possible too. So basically, we just call Anomalib train subcommand, provide the data, provide the model, and it will pretty much do the same thing that this API, this code base does. So it is also possible that let's say you use CLI, but you would like to overwrite some parameters without diving deeper into the code base. So that's also possible. So like basically, you just provide some extra arguments. For example, if you want to use transistor category from MVTech, just pass the category, and it will overwrite all the configuration. So let me just talk about the test and export capabilities. So basically, the same logic. So we have the test entry point either from API or CLI, pass the data module or model, and the test entry point will do the rest. And testing the model, returning the performance numbers, saving the results, and so on. Finally, if you would like to export the model after being happy with the results, so engine has an export entry point as well as the CLI subcommand. So we have multiple export types: Torch, Onyx, or OpenVINO. So the Torch meaning that under the hood we're using PyTorch Lightning, but for those who would like to use pure Torch model, yeah, we can export the model into Torch basically. So these are all the entry points that we currently support, all the way from training to export and the prediction, which completes the machine learning lifecycle. So these are kind of the entry points that a user can just use for models off the shelf, for the data off the shelf. But let me briefly talk about the modules as well. So let's say a user would like to get some benchmark data sets, including MVTech, BeanTech, Visa, or maybe some other video data sets. So what they need to do, just from Anomaly the data, import the data that they're interested in, initialize the data module, and just set it up. And the rest is basically the data module provides train data loader, test data loader, validation data loader, and so on. This is quite similar to PyTorch Lightning's approach. So the user will have access to all the important keys and values, basically. So the same concept for the validation data loader and the test data loader as well. So the data module encapsulates all these data loaders. But let's say a user would like to customize and use Anomalib for their own custom data. So they can do that via folder data set. So provide the root, all the specifics about their data set. And it is possible to train an anomaly detection model in their very much customized or custom data. And the rest is pretty much the same as previously. So train data loader, validation data loader, all the values that the user is interested, it's there. Let me quickly show you the model API. Anomaly provides many state-of-the-art models, as I mentioned. So it's basically whichever model the user would like to use, they can just import it from models and instantiate it from, initialize the model based on the configuration they would like to do. And the rest is pretty much, passing the data to the model and doing the rest of the model operations, basically. But the previous one was for the off-the-shelf models that are supported by Anomalib. But let's say a user would like to create a custom model, design their own. So how is it possible to do that with Anomalib? So, well, the user needs to create two model implementation. One is Torch model, and the other one is the Anomalib model. For the Torch model, it's pretty much a typical standard neural network module that has a forward pass. So autoencoders are quite popular in anomaly detection. So this is currently not available in Anomalib, but we can quickly add this into Anomalib. So basically what we need to do is create an encoder, create a decoder, like within the forward pass, do an encoder, decoder glass shape, and then get the output. And as the next step, we need to implement this my model, or whatever you want to name it, by inheriting this anomaly module, and basically use this torch model here and the loss function if you have any. And the rest is configure optimizers, the training step and validation step. For those who are familiar with the Lightning, this is pretty much the same as PyTorch Lightning, because Anomaly module also utilize Lightning module under the hood. But this is a quite clean approach to add custom models or design a model on your own. So once we add this model into the engine and data modules, like all the functionality, all the cool features of Anomaly will just be supported off the shelf. There are a bunch of metrics that we could also utilize within Anomaly. So for the first bits are quite similar, but what we need to do here is that we need to pass the matrix that we're interested. It's either pixel matrix or image matrix. So this could be F1 score, AR, SAU Pro, or accuracy, precision, whatever the user interested. So the user will pass the matrix, and the rest will be handled by Anomaly. Yeah, so the rest of the stuff is just calling the right entry point. Yeah, so if we just recall this, yeah, this is quite a common applications in industry, as I mentioned. And this demo is created by my colleague Paula, and she used Anomaly for this one, and she trained a pattern model on this data set that she quickly captured with this camera. She trained a model, like a pattern model, I think like a couple of minutes, even on CPU, I think. And she managed to get a quite high 90+% performance. And it just works great. So the model basically picks up the defective parts from the normal or good samples, basically removes it from the conveyor belt. Yeah, this is a demo, a POC, but as I said, it is quite common and has quite a lot of use cases following this approach. All right, so this is quite useful, but when it comes to deploying these models after the training, we have a bunch of problems, like for the deployment setting, there are some data drift that, the data set is not exactly the same as in the lab environment. So, there could be some perturbations like lightning changes, or maybe some noise on the camera, maybe dust on the camera, or maybe camera angle changes when the models are deployed and things like that. So all these sort of the perturbations negatively impacts the overall performance of the models for the real world setting. So this is kind of setting the stage for the challenge that we're organizing or sponsoring at CVPR this year. Maybe I can quickly talk about that one and wrap up my talk. So yeah, we organize two categories at the visual anomaly detection challenge. The first one being that we would like to find some models that are robust to these data drift. So they are, robust in perturbations or some, all these different types of external conditions like lightning or noise and things like that. And the second category is that we would like to utilize large vision models or vision language models within a few shot learning scheme to find out logical and structural defect detection. So I'm going to dive deeper into each of these categories. Right. So yeah, when you look at this image, so we could spot the difference, like the defective parts. So these are kind of similar to the previous slide. We can see that the data distribution is quite similar. The lightning is quite similar. It's a quite nice lab environment. But what happens when these conditions change over time within the deployment setting? So that's kind of the main motivation for the first challenge. So we are looking for some robust models that can tackle these challenges pretty well. Right. So as I mentioned, so the participants are to develop models, based on one class training paradigm. This means that they will only use normal images, but we expect the models to be quite robust on anomalous samples, plus with extra perturbations or some external factors. Right. So that's the first one, and let me quickly go over the second category. So in many times in an industrial setting and in the literature, academic literature, main focus is on the structural defects, but in some cases, there is also logical defects as well. So, like, what do I mean by logical defects? It's basically, there are many cases where structurally the sample might look okay, but logically speaking, there could be something wrong. Like, for example, think about a factory floor where they produce, juice, for example. Let's say they're producing orange juice, but they just label it as an apple juice, for example. There's no structural defect there, but logically it doesn't make sense and it's something wrong, right? So for example, here we have two nuts, two washers, one short screw and one long screw. But when we look at this, on the left, we can see that both of the screws are long. So there's, structurally speaking, there's nothing wrong with this. But, logically speaking, this is missing short screw. So this is a logical defect. On the right-hand side, though, there's a broken short screw. So that kind of shows a structural defect. In the second category, what we want to do or focus on is to kind of differentiate the logical and structural anomalies instead of focusing only on structural anomalies. And we are and also the main focus is utilize VLMs and within a few shot learning paradigm to localize both structural and logical anomalies. And what do I mean by few shot learning? Basically, we don't expect the participants to train on a really large data set, but instead we just want them to utilize a few shot learning. Of course, they can use some pre-trained models, but the main learning type will be the few shot learning. In terms of the data sets, For the first category, we will be utilizing MVTech's anomaly detection dataset, which has 15 categories. And the second category will utilize MVTech Loco anomaly detection dataset. So as I mentioned, it contains both structural anomalies and logical anomalies. And if you could look at this, what do I mean by a logical anomaly? Is that, in this breakfast box, for example, there's something wrong here, logically speaking. If you just, I think these are not proportional enough. There's 2 apples, but there's 2 oranges here. There's 1 apple here. It's not a structural defect, but something wrong logically. And same as screw back and push pins and splicing connectors and juice bottles. So we would like to find out how models tackle structural anomalies as well as logical anomalies. This is kind of quite critical in industrial applications or manufacturing or retail. So the challenge is being hosted on Hackster. So for those who would like to participate in the challenge, so they can just join Hackster and join the challenge here. As of now, I think we have like more than 230 participants and with few submissions. And the final submission will be the 1st of June. So there's still time to, start participating and try something and submit. That's. I think it's a quite fun challenge, I would say. So the leaderboard will be evaluated based on multiple matrix. For the category 1, we will be utilizing image F1 and pixel F1, and the final score will be the harmonic mean of these 2 scores. And for category 2, we will be focusing on image level AUFC. The AUFC meaning that we will be plotting the curve, like F1 score for each K shot, like 1 shot, 2 shot, all the way to 8 shot. And we'll basically measure the area under the F1 curve. And this will be the final score. So there's the submission guideline, but I'm not going to go into the details here. For those who are interested, they can refer to Hackster. There's a detailed submission guidelines there. And the nice thing is that, we're going to be giving prizes for the first and the second place. For the first place, we'll get a Nevis Intel AI PC, which is a quite cool laptop for AI applications and AI on the go. And for the second place, we'll get an Intel Arc GPU. Right, so let me briefly talk about the team. So myself, based in the UK, Dick and Ashwin they are based in Netherlands, and recently Harim joined us, and he's based in Korea. So with 4 engineers, we are behind this Anomalib V1, that's pretty much it. So I'm happy to answer any questions you have in regards to Anomalib or the challenge itself. Thank you very much.
Thank you, Samet. So there is one question, and this was asked during your model slide where you were talking about custom model API definitions. The question was, will this model work on non-image data such as credit card transactions?
It could work. Well, currently in Anomalib, it may not work now because we don't support 1D data at the moment, but we are working on it. So it'll be available on the Anomalib side. So I think within the short term, it'll be available. So I think I would say like within a couple of months, if whoever asked the question, if he or she can check Anomalib, this custom model support would be supported on other domains as well. Yeah.